Welcome back, ladies and gentlemen. Here we go with a video looking into a new topic, waves. Now, waves are all around us. There are many examples of wave-like nature all around us, and I'm sure you're already thinking of a few. But I want to start by looking back a little bit at simple harmonic motion. There's a reason for doing this. So, if you recall, with simple harmonic motion, what we looked at was how something is oscillating over time, right? So its position is changing back and forth. So maybe you have something there back and forth, right? And it will oscillate to a position that's maximum. That'd be the amplitude. The other direction would be the position of negative amplitude. And let's say we pull a pendulum to the side, we displace it to A and let it go. Then over time, you recall it's going to display this cosine-like wave shape, right? And this is all good, and you recognize that there is an important thing happening at this location, and that is a period of time, right? This is your horizontal time axis. Well, what time is that? So that guy represents the time it takes to do one complete oscillation, to start at this location and cycle down to that location here, and then cycle back up to that location there. That's the period of that simple harmonic motion. Awesome. Well, what if we look at that oscillating thing, that oscillating object? In this case, maybe we use a pendulum. And what if we look at that pendulum and what it might do in space if we kind of get that pendulum moving, say have that pendulum traveling in an airplane through the air. What is the bob on the end of the pendulum going to do in terms of tracing out a pattern through space as the plane flies through the air? It might look something like this. So remember, the pendulum is just going to do a back and forth, simple harmonic motion, right? And now the airplane, though, and its flight will sort of be the paper moving this way. We're going to represent the airplane's motion as best I can by dragging the paper horizontally this way while that simple harmonic motion back and forth of the pendulum takes place. So we're going to be able to sort of map out what the bob on the end of the pendulum is going to do, what pattern it will trace out in space as the airplane flies. So I got to get this going back and forth, and I start pulling the paper. And it's far from perfect, you would agree, but you recognize a very similar pattern here, don't you? If I had been careful about the speed of the paper, if I had been careful about my motion back and forth to model simple harmonic motion, then you'd see something very much like this. So now on this graph, if separate these guys from each other a little bit, right? Now this is going to be a different graph. We're going to say, you know what, the movement back and forth of the pendulum, well, that's now going to represent something in, let's say, this direction, which is the y direction. And then the movement of the airplane sideways, well, that might be motion in the x direction. So this is like position in one dimension compared to position in another dimension, x versus y. We're tracing out the pattern that the pendulum took. And what we see is just like this. It's the same shape. Ooh, we got a little weird with that one, but you get the idea. So look at this. There's a distance from here to here, right? That distance is still amplitude. So this location out here is still A. And so you'd have negative A down here still. And we could draw amplitude out here because this is, if you look at the height of that wave, of that curve there. That's still amplitude there. We can draw amplitude out here if you want. That's still amplitude away. This is, by the way, still amplitude, just in the negative direction. But check this out. Now we're no longer measuring the time it takes to complete one oscillation. When we go from here back there, it's covered a distance, not a time. So from there to there. It's now a distance. And so if you look at this, this is a distance to do what? A distance to go from here and oscillate there and come back to the starting position. So we completed one wave, essentially. So this distance is the length of that wave. So you call that a wavelength. That's where the term wavelength comes from. Awesome. And there's a whole bunch of other stuff, some terminology that we need to get to here regarding waves. So let's take a look at that. So let me bring back an example here, a diagram we can look at. And so there is an amplitude to a wave, absolutely. There is a wavelength to a wave. There's a certain symbol that we use for wavelength, and it's a Greek letter lambda. So there's your wavelength. And A is amplitude. Okay, cool. Well, there's some other stuff going on as well. That you'll read about these terms, you'll hear these terms from time to time, and you want to be familiar with them. So at the peak right here is a crest of the wave. It's like a high point. And at the bottom right here, this low point is a trough. And there are crests and troughs all over the place. It depends on for how much distance you travel or distance you monitor the wave. And you've got wavelength from one crest to another. Well, guess what? You've also got wavelength from one trough to another. That is also a wavelength. It doesn't matter where you start measuring as long as you stop measuring at a corresponding matching location. So from trough to trough, from crest to crest, you could say, you know what? I'm going to measure a wavelength. From here, I'm on the downswing, so to speak, or the swing toward the negative direction, and I'm going to complete one wavelength. So down, and I got to go to there. That would also be one wavelength. Right there. Okay, and there's something interesting here. Well, what are we talking about? I remember with the pendulum in the airplane. Well, that's not really what waves are all about. Essentially, if you've ever done something like drop a stone into a pond and you watch the ripples in the water surface move outward in all directions, looks like those circular waves, right? Well, those are waves. So we look at that, the ripples in the pond, and we have to recognize, okay, the water isn't going anywhere, is it? Same thing with waves of the ocean. Same thing with seismic waves traveling through the Earth's crust. Same thing with a human wave in a stadium at a sporting event where people stand up, put their arms in the air, and sit back down. Well, you know what? As that wave goes around and around the stadium, the people don't go anywhere. They don't change their locations, do they? So with waves, the thing the wave is traveling through doesn't go anywhere. It oscillates, right? So that's why we can tie this back to simple harmonic motion, because there is oscillation taking place. The people in the stadium, they stand up and they sit back down. And they might do it again. They stand up and they sit back down. But they don't go anywhere. The wave itself does. So what is a wave if it's not the same as the medium that it's traveling through? Here you go. Here's your definition of a wave. It's a disturbance in the medium. Now, when we say medium, it just means whatever the stuff is that the wave is traveling through, right? So a disturbance in the medium, that propagates from one place to another. Well, propagates is just a fancy word for goes somewhere. It just propagates from one place to another. So a medium, the stuff it's traveling through. Propagates, it goes somewhere. Not the stuff, but the wave. So how did the wave happen in the first place? How did it come about that there is a disturbance? Well, you had to have some energy, some work done, right? What disturbed the people in the stands, in the bleachers or in the stadium, right? Well, they exerted energy. They did some work, and they stood up and they sat back down. There was disturbance in the medium, and it's the disturbance that travels somewhere. That's important. It's that disturbance. And therefore, what do waves do? Essentially, waves carry energy from one place to another. That's a great way to remember this. They carry energy. They transport energy from one place to another. And so it isn't, in the water. It isn't the water that goes somewhere else. But it took energy to create the wave. And that energy ends up going somewhere. And that energy can do something. For example, it can cause erosion on a shoreline. It can propel a surfer. All kinds of things. But it's just energy going somewhere. That's that disturbance. That disturbance is the energy. Okay. Well, we need to look at some different kinds of waves also. There are different kinds. I've mentioned several. So let's get scientific about this. Types of waves. Okay. So here we go. I want to show you something, right? So we've got this guy, and I'll let him loose a little bit. Oh, you even saw something right there. Check this out. I'll do that again. Whoa, that looked like something traveling down the length of that, the slinky here. Well, I could wiggle this end up and down, right? And there's a short distance here, so it happens kind of fast. But you see what looks like the bump, the crest, travel this way down the length of the slinky. And that kind of wave, where the disturbance seems to be up and down, but the wave is traveling left and right. The disturbance is perpendicular to the direction of the wave. That's important to understand. The disturbance is up and down, and you get these peaks and troughs, or crests and troughs, right? That's one kind of wave, and that kind is called a transverse wave. And it's real simple definition. A transverse wave, the disturbance is perpendicular to the direction of the wave. Or the wave's motion. So a wave is moving, the energy is moving somewhere. And what we see here is we see a bunch of perpendicular disturbances, right? And we can model this in class much better than this tiny space here. There's another kind of wave. There's transverse. And transverse really would be the same as you shaking the end of a rope up and down. And there's a really good picture of this in your book. But essentially, the waves are traveling in one direction, but the disturbance is perpendicular to that. One part of that medium, the medium is the rope, let's say, or the slinky. It's being disturbed this way, but the wave travels this way. Okay, that's transverse. Well, kind of the opposite of transverse, you're going to have what's called longitudinal. Longitudinal waves. Okay. Well, the disturbance for a longitudinal wave is parallel to the wave's motion. All right, so what's that going to look like? Well, that was the first thing you saw when I was first setting this up, and I kind of had things happen like this. And the disturbance, what I can do is I can let go of some of these coils. And you actually see, it happens kind of fast, but you see it traveling up and down. But what's the disturbance? The disturbance is I've got I've got medium that's coiled real tightly and medium that's coiled very open and loose, or you might say it's not very dense here. And I let go, and these coils want to open. But as those open, the coils immediately in front of them have to get closer together. And it kind of works out like that. And this compression right here, well, those want to expand again. And so as those expand, the coils right in front want to compress. And the compression ends up traveling down the length. But you can see also the disturbance is in that same direction. So, how do we draw that? We have some coil. And now some of it is very closely spaced, and then some of it is very open, and then closely spaced, and then open, and then closely spaced, and then open, and so on. So here's the deal. I'll use a different color for this so it stands out just a little better. You know that the wave is still traveling this way. Okay. But now, look at what's happening to any part of this medium. Let me pick this part, right here. That part of the slinky is oscillating that way and that way. So the oscillation, the disturbance, is now parallel to the direction of the wave. And I'll show you that one more time. Longitudinal waves are probably neater than transverse waves. So here we go. I'll let loose a couple of the coils on the right side here. And you notice something else. You saw the wave travel to the left, but you noticed that it seemed to bounce back to the right. A little bit anyway. There's losses of energy due to friction, pretty significant losses, and that's why it just kind of disappears. Okay, but you've got transverse and longitudinal waves. There's also a category of wave called surface waves, and they are different. So you have transverse, you have longitudinal, and you have surface waves. Well, surface waves are just that. Waves traveling along the surface of something, surface of the water. Across the surface of Earth's crust, you have surface seismic waves, for sure. The surface of anything, really. And they behave a little differently, but they still follow some fundamental ideas here. On the surface, a particle at the surface is disturbed. It doesn't go anywhere. It doesn't travel anywhere because of the wave. And it sort of does oscillate. But there's some subtle differences here. So look at, if we imagine water. Then what happens is, as the wave travels down this way, we'll look at this crest, a particle at the surface, here, as the wave travels, the particle is actually going to sort of, you imagine it sliding down the back side of that crest. And that's true. So the particle actually traces out a circular path in space as the waves come and go. I kind of drew that circle a little too big, because really what you have going on is, if you have waves along the surface of water, then at the level of the trough to the level of the crest, right? There's our particle. That's where this pathway, the circular pathway, is. It's just doing that, and it just keeps doing that. And so that particle doesn't travel anywhere. It just keeps coming back to that same spot, same spot, same spot. Things under the surface are a little different, a little more complicated. Not too bad, but we're not going to worry about that right now. Okay, so got types of waves. Well, next, uh, there's a big idea. We've been talking about waves traveling somewhere, right? So if you watch one crest, it's going to look like the crest just kind of slides sideways. That's what we saw with our, not that guy, this guy. So we saw with this. I mean, if you just imagine, it looks like the crest is just sliding like that. Well, if the wave is traveling anywhere, it can be said to have a velocity, right? So this idea of the speed of the wave. Well, look at this. Look at what's happening. I'll bring this one back. How do we get speed out of this? Well, look. If I had lined this up better, it'd be more evident. You have a length of a wave. There's a distance in a period of time. One wavelength in one period. Well, that's a distance and that's a time. If we just do a division, we get a speed. So, speed of a wave. You can say that you're going to find that by finding the wavelength and divide by the period. That should be really straightforward, okay? We're just using different notation now for our distance and our time. No big deal. But there's a little more. Remember that period is simply the inverse of frequency. We're seeing that come back. So we can say that, well, velocity or speed of the wave is also equivalent to wavelength times frequency. Okay, that's a big, big deal. This right here, it's very important, very fundamental to all waves, okay? But there's more, of course, there's more. When we look at something like the speed of a wave in a string, if you imagine a guitar with the strings on it, and you disturb the string, you just pluck the string, there's going to be a wave traveling down the string. Okay, now this is specific to waves on a string or rope, but you've already had a hint of this. So the velocity or the speed of that wave on the string, it sort of depends on the tension that's in that string, and I can sort of illustrate that here. Watch this. There's not a lot of tension. I'm not pulling these coils really far apart. There's low amount of tension here, and I will create a longitudinal wave. And you saw how fast it went. I'll do it one more time. Watch how fast it goes. Okay, now I'm going to create much more tension, and I'll create another longitudinal wave. And watch how fast this one goes. Okay. Whoa. Do it again. More tension. Okay. Less tension. Even less tension. So the speed of a wave on a string seems to be somehow connected to the amount of tension. And there's more though. If you imagine, instead of lightweight plastic like this stuff, if you imagine it's a very heavy, thick rope or even metal cable with a lot of mass to it, well, the more mass there is, the harder it's going to be to disturb it up and down. And so the wave is actually going to move slower. It turns out, when you get into this, that the speed of a wave on a string is directly proportional to the square root of the force of tension in the string, and inversely proportional to the square root of this thing called mass per unit length. It's just the symbol mu, and we say where that is equal to mass per unit length. So it doesn't matter how much total mass we have. What matters is sort of the density of that mass. A centimeter of it, a meter of it, a kilometer of it, whatever. What is the mass of that length of it? And that value is this guy right here. So the larger the mass, the smaller the speed of the wave in that string. You use a lighter, thinner string, the wave will travel faster. Use a thicker, heavier string or rope or cable, and the wave will travel slower. Awesome. Well, we can connect those two ideas about speed, these two right here. So, velocity of the wave, we've got that or that. And we also have speed of the wave as this. And of course, they're equal to the same thing. We can connect them. And you can say, well, almost anything you want. You can say, well, if we're dealing with a string, force of tension, I should put a T there, sorry. Force of tension divided by mass per unit length. And we can equate that to wavelength times frequency if you want. If you know the speed and some other information, you can mix all these together. You can find out just about anything you want, assuming you have enough information, right? So it's worth doing. We're essentially connecting mass per unit length. We are connecting force of tension. To those we are relating wavelength. We are relating the period of the wave. We are relating frequency of the wave, and also the wave speed. All these things in that one tiny little bundle of those two equations, essentially these two right here. Boom, boom. And they apply to all waves. They're very fundamental to studying waves of any kind. Right? So you want to be familiar with the terms. What are some other terms we looked at? Crest and trough, period, wavelength. What else did we see? We saw how you can look at a wave as just an oscillation over time, but this is a different graph now. For the wave itself, it's an oscillation across a distance now, right? Okay, so that wraps it up for this video. Try to keep it short and sweet. More are coming. Thanks for watching. I'll catch you next time.